What the heck is up, guys? It's Jacob here, and in this video we're going to be talking about resistance. So this is probably just going to be a really short video. It's not really too complex, not a hard idea to understand. So this is resistance. So resistance is basically a measurement of how much a conductor resists the flow of current. So to understand what current is and all that, you're going to have to go back and watch the current video. You won't understand what that is unless you watch the current video. But basically, what we have when a current is flowing, we have these little charges flowing, and you can see these arrows indicating that there's electrons flowing from shell to shell of these atoms. And basically, the resistance is measuring kind of how much these conductors, how good these conductors are at conducting these electrons, at allowing these electrons to flow. And the more resistance you have, really the harder it is for these electrons to flow, and the more collisions, as we can see here, the more collisions we're going to have. And really, it's just going to kind of slow down the flow of these electrons. It's not going to allow as much current to flow, because there's going to be so many collisions that it's going to produce heat, and it's going to just really slow down these charge carriers from flowing. So it's not as good of a conductor with the more resistance you have. So let's clear that. The SI unit for resistance is ohms. So the ohm is the unit of resistance. It's just a measurement of how good a conductor conducts electricity. So again, the higher the resistance, the more it resists current flow, and the worse of a conductor it is. And the lower the resistance, the better of a conductor it is, the less it resists the flow of current, and the less collisions here we'll have, the more efficient of a conductor that conductor will be. So again, well, let's look at resistance and current losses. I've explained this kind of in my current video. A conductor with less resistance on the top, and then we have on the bottom a conductor with more resistance. So we can see basically a conductor with less resistance has less of these little collisions here, whereas a conductor with more resistance has more of these collisions here. And we can see there's a lot more collisions, there's a lot more heat, and it doesn't allow as much current to flow. Although I shouldn't have put as many arrows, because it looks like there's the same amount of current flowing. There's not really the same amount of current flowing. Assuming there's the same potential difference across these conductors, there would not be the same amount of current flowing. And even if there was a different potential difference and we had the same amount of current flowing, you can see there's more heat being emitted. So these conductors, the top one would be a lot more efficient conductor. It would allow current to flow less, easier, and it would have less of an impedance, or it would have less of a resistance against that flow. Whereas this bottom conductor has more collisions, and it resists that flow. It's harder for that current to flow, and it generates more heat, and there's losses. And sometimes this can be a good thing. As I explained before, this is what's known as Joule heating, and it can be used for heating elements and things like that. This is actually the only process that really is actually 100% efficient. I mean, you should be really wary anytime you hear something is 100% efficient. Really, there's no such thing as 100% efficiency. But in this case, this is one of those processes that is actually 100% efficient, because typically any process you have is not 100% efficient, because there's losses that are perceived as heat. Typically, you have losses that are eventually are heat losses. And in this case, if you're going for a heating element, that's all you have here is just heat losses. That's all it is just heat. So a heating element really is the only electronic component that's actually 100% efficient, because any losses are just going to contribute to more heat. So there really are technically no losses in a heating element. But typically, like in just a conductor, or let's just say something like an extension cord, if you had it plugged into a high power appliance, there's that extension cord is going to warm up due to the resistance in that cable, as we see here, and the collisions that actually happen between the electrons in that wire, and that will result in losses, and those are unwanted losses typically. So that's why we're talking about resistance and current losses, and that's why those are typically associated with each other. So now let's look at some factors which actually affect resistance. So there are really three factors that affect resistance. And I didn't really want to put any formulas in these videos, because I didn't really want to have any actual math involved. I just wanted them to be like mainly conceptual. But this formula actually has like a really good conceptual element to it, so I thought I'd throw it in here. So basically, this formula is what affects the resistance. So this R is the resistance, and as we can see, it's directly proportional to these two top elements, which one of them is resistivity, and that is that's a material constant. So the units for that is actually ohm meters, and you can actually go online and look up the resistivity of just about any material. So like iron will have a resistivity, copper will have a resistivity, silver will have a resistivity, and basically, because it's directly proportional to it, the more the resistivity, the more it resists currents, and the higher your resistance will be. And also, the resistance is directly proportional to the conductor length. So when the length gets larger, your resistance goes up, which kind of makes sense, right? Because if you have a material, right, that's actually a resistor, and it has some resistivity to it, the more of that material you have to go through, or the longer length you have to go through, the more your resistance is going to be. Your resistance is going to go up the longer this conductor is. And we can see that here. This L represents the length. So if you have a wire and it has a certain resistivity, that conductor has a resistivity to it, the longer that wire is, the greater the resistance is. And the shorter that wire is, the less your resistance overall will be. And then also, so the resistance is inversely proportional to the cross-sectional area. So that's the area of the conductor. That's what we can see here. So like if you were to find the area of this conductor, this circle, that will tell you the cross-sectional area, and it's inversely proportional to that. So the larger the area you have, the less resistance you have. The smaller the area you have, the more resistance you have, which kind of makes sense. I mean, if you think about it intuitively, it's very not too hard to think about, because if you have some conductor that's resisting the flow of electricity, if you have a larger conductor, right, if this conductor is actually larger, the area of that conductor is larger, you have more paths, you have more area for those electrons to flow, for that current to flow. If you reduce that cross-sectional area, if you make it smaller, there is less of an area for those electrons to flow. There's less cross-sectional area for that current to actually flow through. So it's going to resist the current more. In this one, the water analogy actually does work really good here. I gotta say, imagine it like, this is really poorly drawn, but if you have like a pipe, and then now all of a sudden your pipe gets thinner. I know I've been kind of beefing on the water analogy this entire time, but it works really good in this case. And you can think of current as kind of like a fluid in this case. So if you have a larger pipe, more current can flow through here, more water can flow through here. And when you reduce the size of that pipe, now you can only have so much water flowing through. It's kind of the same idea here. So the larger your area, the less of a resistance, the more current can flow. And those are the three factors which influence the resistance of a conductor: is the actual material it's made out of, or the resistivity of that material, the length of the conductor, and how much area. And this is only, the area is only as good as the weakest link. So if you have a really big area and then it reduces down to a small area, that area is going to be what's going to determine the resistance of that conductor. And also, basically these three factors tuned really tightly is what makes up the actual resistor component. If you've ever seen like an electronic resistor, a resistor is just made up of a specific material, like a carbon film resistor or a metal film resistor. They basically take a conductor with a very precise, or a very, they know the resistivity of that conductor very well, and then what they do is they wrap that conductor around the resistor to a very precise length. They know the exact length that conductor will be wrapped into that resistor, and then they make that conductor a very small or a very precise cross-sectional area. So they control those three factors very tightly, and they can get basically an element inside that resistor, a wire or a piece of carbon or whatever that material is. They can get that to add up to basically a very precise resistance, and they can get that resistance tightly controlled. And that's how you get something like a 1K resistor or a 10K resistor or whatever. They take these three factors and they kind of control them in such a tight manner that they can actually get a resistor that's 1K plus or minus 5%. And that's how resistors are made, is just by finding a material and wrapping that resistor, that material around that resistor in a specified length, and they only give it a certain cross-sectional area, and that gives a very specific resistance. And that's pretty much it. There's not really much more to resistors. They're very basic. The resistance is just a very basic concept to understand. It's not complex at all. So that pretty much wraps up for this one, guys. I hope you enjoyed it, and as always, have a good one.